Hello students, today I shall be talking on cardinality or cardinal number of a set. What is cardinality? If a set is finite, then either it is empty, that is null set, or it contains a finite number of elements. This is the definition of finite set. So the cardinality of a finite set is defined as the number of elements in the set. If the set is finite, we can count the number of elements, and this number of elements in the set is called cardinality or cardinal number of the set. And if the set is A, it is denoted by Na, n first bracketed A, or sometimes it is also denoted by this symbol looking like mod A, but we shall call it cardinality of a number of elements in the set A. But very often we shall use Na, small n first bracketed A, read it cardinality of A or number of elements in the set A. So definition is Na equal to number of elements in the set A. In a set we know repetition is not allowed. One object is kept once only, so all the elements are distinct, and therefore number of elements in the set, a finite set, is a unique number, definite number. So that is called cardinality of the set. For example, if capital A is the set of all vowels in English alphabet, A, E, I, O, U, then we see that there are 5 vowels, 5 elements in this set, and that's why Na equal to 5. Another example, if we consider B a set containing only the element 2, this is a singleton set, it contains only one element. So NB, number of elements in the set B or cardinality of B is 1. Another example, if we consider the set C as the set of all natural numbers up to 99, starting from 1 up to 99. So there are 99 numbers of natural numbers, that's why NC equal to 99. 99 number of distinct elements in this set. Another set, if we consider D in set builder form, X such that X is a prime number less than 20. Then to find ND, we should list the elements. Otherwise, you cannot tell the number. So prime numbers less than 20 are 2, 3, 5, 7, 11, 13, 17, 19. These are the only prime numbers less than 20, and they are 8 in number. So ND equal to 8. So this is cardinality, and of course for an infinite set also cardinality is defined, but in our syllabus in class 11 it is not included. Later we shall see when if we study degree course, cardinality of infinite set. Now one theorem. Now the theorem concerning cardinality. For any two finite sets, capital A and B are two finite sets, then NA union B. What is union we know? NA union B is NA plus NB minus NA intersection. That is number of elements in the union of two sets A and B is equal to number of elements in the set A plus number of elements in the set B minus number of elements in the set A intersection B. So proof, very easy. If we look into the Venn diagram, still the proof is asked with 3 marks or 4 marks. That's why some details we want to write. NA union B by definition is number of elements in A union B is equal to number of elements in A plus number of elements in B which are not in A, because A and B may have common elements. We cannot count an element 2 times. See in the Venn diagram, suppose A is the set containing this red dots are the elements. Suppose 1, 2, 3, 4, 5, 6, 7, 8. 8 elements A contains, and B contains 1, 2, 3, 4, 5, 6, 7 elements. You cannot say that A union B contains 15 elements, 8 plus 7, because in that case these 3 elements which are common to both A and B are counted twice. So you cannot count twice. That's why number of elements in A union B ultimately becomes number of elements in A plus number of elements in B which are not in A, that is which are not common to both the sets. So it is Na plus number of elements in A is Na plus number of elements in B minus A. See, this shaded portion is B minus A. Means elements in B but not in A. That is not in A intersection B. So number of elements in B minus A. And number of elements in B minus A is nothing but number of elements in B minus number of common elements. So it is number of elements in B minus A. We have written number of elements in B minus number of elements in both A and B. So that is number of elements in B means NB. So Na plus NB minus number of elements in both A and B means number of elements in A intersection B. And by definition this is an A intersection. So the result is proved. Very obvious from Venn diagram. Still we have written few lines. Now particular case, if A intersection B equal to phi, now set A and B are disjoint, no common elements. In that case, Na intersection B is n phi. N phi means phi is the null set, means containing no elements. So n phi equal to 0. This is an important result also. N phi, cardinality of null set is what? 0. So ultimately in this case Na union B becomes Na plus NB only. So this is the result concerning cardinality of union of two sets. And now we shall see for three sets extending. Now let us see another theorem. Extension of previous one. Extension of previous one for three finite sets. Suppose A, B, C are three finite sets. Then N A union B union C. N A union B union C is Na plus NB plus NC. Minus N A intersection B, minus N B intersection C, minus N C intersection A, or you can write A intersection C, plus N A intersection B intersection C. Proof. Already we have proved. So you have written instead of AB, just I have written the result for P and Q. For any two finite sets P and Q, we have NP union Q equal to NP plus NQ minus NP intersection Q. Instead of AB, only with PQ I have written. Now we shall apply this result again and again. So N A union B union C can be written as N A union B union C associative. We can give bracket anywhere, first two or last two. I have given bracket to the last two. You can do with first two. So this is as if NP union Q. So it is NP plus NQ minus NP intersection Q. Here P is A and Q is B union C. So this Na plus NB union C, again you can consider it as P union Q. So it will be NB plus NC minus NB intersection C. Now this A intersection B union C, by distributive law we can write Na intersection B union N union A intersection C, distributive. Now Na plus NB plus NC, then this remains. Here again you can consider it as NP union Q. So NP plus NQ minus NP intersection Q. Here P is A intersection B, Q is A intersection C. So other things remaining, say here it is minus NA intersection B minus NA intersection C, and this A intersection B intersection A intersection C, actually it can be written as only A intersection B intersection C. A intersection A, by commutative property we can bring here A intersection A will be again A. So ultimately one A to be kept. So finally we have written systematically Na plus NB plus NC minus Na intersection B, NB intersection C, and A intersection C, written only C intersection A commutative, and lastly this remains. So this is the result proved for three sets with the help of first result. So likewise we can extend also, but up to this is sufficient for our class 11. So thank you for today.